think I'm live. I might be live. I think I'm live. Yeah, so just let me copy some stuff and then we can go ahead and do some stuff, do some exploring. This is live. Hello everyone. Hello Bartolomeo. Hello everyone. I've been away for a bit. I've been a little busy at work. I've got some. I had to do some. I had to do quite a bit of video work, quite a bit of development, and you might see that my background is a little different. I might look a little different. We're still sorting out lighting in my new lab, in my new office. So that's pretty cool, and yeah, we should have that going soon. Why is that? Why is it unlisted? Sorry. Somehow this stream is unlisted. It should be public. Cool. So yeah, so that's public, and anyone should be able to see this now. So, what are we doing today? What I want to explore today is there's a new RFC from Bang of NXP, and we want to explore what the new developments in media on Zephyr, and hopefully we can get to a point where we run a sample. But even if we don't get to a point where we run a sample, we should at least get a handle of what's going on so that we understand what we want to do, really. So we're gonna go through a pull request, and we're gonna explore some stuff, and we're gonna learn some stuff, and maybe if we're lucky at the end, we're gonna run some samples. I have a very sort of complicated setup in front of me right now that doesn't really work, but I do have a setup that should work, and we'll see. I don't like moving it because basically, how do I say this? I don't like moving it because I might lose a wire or something, and then that's a problem. But for now, let's actually just explore. So Zephyr has a new, basically it's a pull request, but really it's a request for comments, and it's a proposal for a new media pipe library. And what we'll just learn shortly of what a media pipe library is, and it's basically things that do arbitration automatically for stuff. So a few streams back, we would have worked on the FRDM MCX N236, and when we worked on that, we realized that the camera wanted a certain resolution, and the interface, SDMA, Smart DMA, wanted a certain resolution, and Zephyr was getting confused between both of them, and it didn't know what to choose. So what basically the media pipe library is introduces a way for all of these little subsystems to speak and communicate and share stuff, so that they can actually all work together in a way that is possible, if that makes any sense. So I'm just gonna go read through this thing, and then as we go along, we'll just explore and we'll learn, and we'll see what happens. Yeah. Do let me know if the stream is buggy or my audio is unaudible or something of the sort, and then we kind of just comment or leave a message on Discord or whichever way, so that we can communicate. So I'm going to start by reading this, and then we're going to look at an image, and then we're going to try and we're not going to really look at the code today. There is a lot of code changes. They're all very small. Sometimes they're very new. And I think since the code is being reviewed by people who work on the code a lot more often than I do, I think the best way is to just try and use it. Try and understand what it is and try and use it. Because going through 95 files of code is going to be difficult without a lot of context and video and audio and all of those things. So I think the best way is to the best thing we can do on this stream is to just try and use it and see if that changes. Then yeah, it could only be louder, so the voice could only be louder. I don't know. Let me see. Let me see if I can if I can increase my audio volume. I hope I don't make it like super loud. So that. Okay, my mic is almost maxed out and it's getting to like the orange parts. So Bartholomew, you let me know if it's too loud, but it's almost maxed out now. Cool. Welcome, Bartholomew, as always. Thank you so much. Very encouraging to have you around. So let's read through this thing by fee, and then we can do some questions and some discussions and maybe run some stuff. So in Zephyr today, multimedia applications such as those involving video, audio, display, visual, and graphics are typically implemented as simple domain-specific applications. While these are sufficient for basic use cases, they quickly become inadequate when dealing with complex processing chains, multiple processing components between a camera and a display, cross-domain scenarios like MPEG-DASH player handling video, audio, subtitles stream over a network with dynamic resolution changes. So basically, what Fee is saying is, and this is something that I've alluded to, especially if you're on the Discord server. I've discussed this quite a bit. Zephyr has all of these individual components. You can use a microphone on Zephyr. You can use an image sensor on Zephyr. You can use a display on Zephyr. But you can't do stuff that requires you to use all of them together. Well, you can, but you would have to sort of you have to do it in a very hacky way, where you have to connect single pipes and control them by yourself, and it becomes very cumbersome very quickly and becomes very complicated very quickly. And Bartholomew, who's worked on quite a bit of audio with me, understands this quite well, because there's not a real way of streaming audio. You can sort of like access audio packets and then you can do something with them. So if you wanted, say, like audio to stream from a microphone all the way to a speaker in Zephyr, it would be a little difficult, because you can get the audio and you can play the audio, but you can't really get the audio, pass it through Zephyr and then play it on this side. That's sort of what we are alluding to here. And basically, what LibMP does is introduces this subsystem sort of thing. I'm not so sure if it's a subsystem yet, but I think I saw downwards in the reviews that it is some sort of subsystem. So it sort of introduces this sort of subsystem where you can, how do we say this? Where you can do all of this media stuff and then you can mangle stuff together and basically use it together. That's basically what LibMP does. And then in such cases, application complexity increases significantly. Developers must manually manage buffer allocation, queuing, dequeuing for each component, as well as synchronization between components across the pipeline, and moreover, similar functionality often needs to be reimplemented across projects, leading to duplicated effort. I think Bartholomew is going to be very familiar with this. I think there's a week somewhere in the last month or two where we were working on audio with Bartholomew almost every day, and it got to a point where we would spend a whole week trying to figure out queuing, dequeuing, processing, and passing over things of the sort. And now things like LibMP, the media pipeline, LibMediaPipe, what they do is they introduce a way for you to say, give me audio of this bitrate from that device now. Not give me packets, not give me samples, give me audio. And it's all of this joining of all of this systems that already exist, so that they all play, they do an interplay together very well. And this is basically what LibMediaMP basically introduces. And we'll look at a sample just now. So it wants to reduce all of this duplicated effort, the queuing, stacking, destacking, sampling, and all of those. You get audio ADC samples. Same with the image sensor. You get ADC samples from an image sensor, and then you mangle them into some sort of image pixel format, and then you send that pixel format to some sort of buffer, and then that buffer is sent to some display of some sort, and then that display finally displays the buffer that you've given into it. So what LibMedia Pipe wants to do is it wants to enable you to do all of these things at once instead of doing them individually and multiple times throughout your progress. Okay, so to address these challenges, this PR introduces LibMedia Pipe, a lightweight multimedia framework designed specifically for Zephyr, natively for Zephyr. I might add specifically for by Fee from NXP. And there's been a few talks about this. So if you go to Linux Foundation YouTube, let's actually do the stream the way we normally do it. So if you go to the Linux Foundation YouTube, and then there should be a Zephyr playlist from the, how do I say this? There should be a Zephyr playlist from the last, how do I say it? Embedded EOSS, Embedded Conference. And that Zephyr playlist will have, we'll have, what do you call? There's going to be some videos about, there's going to be a presentation by Fee on Open Source Summit. Cool, thank you so much. Actually, Open Source Summit. Yeah, this one. So if you go here, actually it's much easier if we go here, and then we can go to there, Open Source Summit, not North America. I want the, what was it? Where was it? Where was the one in, where was the Europe one? Remind me. Which city was the Europe one? I think it was Berlin or something. Can we search for Zephyr? Zephyr. Let's see if we can search for Zephyr. Yeah, Open Source Summit, not another. I think, it was in Prague. Yeah, if I remember correctly. Was it Prague? Yeah, this was the one. I think so. And then I think if we look at the agenda, if you want to go look at the agenda. No, this is in 2026. I want the ones that are past. I want the 2025 one. Open Source Summit, I don't know where it was. The last one. There was a 25 one. There was one in Europe. And in that, you're going to find a playlist. This video. I think Bartholomew is going to share. Bartholomew is going to share a link, and I'm going to share it on the stream. So yeah, Bartholomew is just going to share a link right now. Thank you so much, Bartholomew. There's a place where Fee introduces this and talks about it very intensely, and he introduces it quite well. And there's also a number of Amsterdam, Open Source Summit Amsterdam. Thank you, Bartholomew. Yeah. Now this one you wanna go, yes, perfect. And then I can choose Zephyr. Probably can't choose Zephyr here. I could probably choose Zephyr Developer Summit, and this should give you, yeah, by the way, another thing, if you want to look at all the videos from the Zephyr Developer Summit and learn some stuff about Zephyr, this is a good thing. There's a lot of good presentations here, and it really is good. It really is good. So let's actually go and find LibMP. I'm not so sure where it was, but it's somewhere here. No, not SOF. LibMP. wasn't a lightning talk video for Zephyr. Yeah, here it is. So there's this video. There's this video. If you, I will copy paste it into the. I shall put it in the description because we don't know how. ZDS link. I'm gonna put it in the description now because the comments sometimes don't show up. So cool. So that's really it. And then I think if I understand correctly, there should be some sort of presentation here. Yes, perfect. So this is actually even better. So because now we can have this and then we can go through this, then we can go and actually run some code. So video for Zephyr. From basic APIs towards a fully fledged video subsystem, or rather, I think the better way to say it is a media subsystem, because it's going to have audio and it's going to have display. And basically, if you have video, you're going to have audio, and if you have audio and video, you're going to have display somehow. So this is kind of what we are going to look at. And then how many pages is this? So why is the PR so huge? Paul. Nice, Paul. Nice to see you around. It's been what, 5 years since you attended a stream of mine? Because it introduces a lot of little changes. Actually, most of the changes you will realize they're not really that huge. They're very small changes. There's a lot of It's a lot of small changes. Everywhere, all over the place, and that's why it's 95 files. Why is that PR so huge? 95 plus changes. So there's this like 10 here, 3 there, 4 there, 5 here. Let's actually explore something before we keep going. So if you guys have done any sort of embedded development, you will learn that if anyone has done any sort of like bare metal development, you will realize that you have to make, say you wanted to use let's put a little example. This is good. This is why I do the streams. So this is an OV7670 camera. So let's think about how to use this in bare metal before we even go before we start using something like an operating system. How would we use this camera in bare metal? Let's say we have this camera and this device. We have this camera and this STM32F4, and we just wanted to do bare metal stuff. The first thing you would need to do is you would need to develop GPIO drivers so that you can actually use the GPIOs to connect to the camera. And then on top of those GPIO drivers, you're probably going to need something like an interrupt controller driver so that you can actually use interrupts you can send interrupts between, like, because you're not going to be able to do video with polling. You're going to have, like, the frame rates are like 60 frames per second or something like that. It's a very, it's a very intensive thing. So you're not going to manage to do polling. So you're going to need GPIO drivers. You're going to need, actually, this is a good segue. Let's go to my GitHub and see if I can actually give you guys a sample. As usual, my mouse always dies during streams. GitHub Zach. So let's go to my GitHub and then let's actually consider something. STM32F4 drivers. So these are drivers for this board from scratch. Okay. So the first thing you would need to do is you would need to build, let's go to the sources. The first thing you need to do, you would need to build GPIO drivers. So GPIO drivers is drivers that will enable you to handle the pins themselves. Okay. And then on top of these GPIO drivers, you would need to come and do something, you need to come and do, I think I usually put them at the bottom. Yes. You would need to come and do interrupt controlling, which is also a driver in itself in some sort, because ARM devices have something called the NVIC, Nested Vector Interrupt Controller. So it's this multiplexer of interrupt controllers that sends interrupt to whatever pin you want. Okay, so you have a GPIO driver, you have a GPIO driver, and then you have a interrupt controller. And then the next thing after that, so this particular device, if I recall correctly, has something called a video interface. Let's actually go to that device's. Let's go to that device's datasheet and we look at it. Not datasheet, reference manual. So give me a reference manual. So let's go and look at it. So in here, it might even be better to look through the reference manual. So first of all, you're going to do what is it? GPIO drivers. Where's GPIO drivers? GPIO. Come on. Don't rush that. So general GPIO. Okay, you're gonna do general purpose input output drivers. Okay, that's number one, the first driver you're gonna build. The second driver you're going to build after that is a nested vector interrupt NVIC controller. There's going to be some sort of maybe here or something. There's going to be a vector interrupt controller driver. So you can now use GPIO pins, you can use interrupts. On top of that, in order to use this camera, so this camera, if you see, I won't be able to show it, so it's easier if I just pull it up, OV7670. This will actually make a lot more sense this way. OV7670, yeah, this one. Let's open here. I just want to get a good image for it. Just a nice image, yeah. So if you look at the pinout for this camera, you will realize that it uses what is this? SIOC, SIOD. So that's SCCB clock, SCCB data. SCCB data clock. SCCB is basically pin for pin and protocol compatible with I2C. So you need GPIO drivers, you need nested vector interrupt controller drivers, and then you're going to also need I2C. Where is I2C? There's the interrupts drivers. Cool. And then you're going to need I2C, IIC, inter, yeah. You're good. So this is the third driver. You've not even gotten to using the camera in itself. This is the third driver. You're going to need the I2C drivers so that you can actually you can send control signals to the camera. Okay, step 3, the next bunch of interrupt. And each driver that I'm speaking about is around like 1,000 lines of code. Okay. Then the next driver you're going to need to build is going to be a DCMI driver, which is a digital camera interface. Bartholomew, remind me, what does DCMI mean? Digital camera interface. That might be it. Let me find it. Yeah, DCMI. There it is. So that's the third driver. We've not even started the camera. Okay, cool. So you need GPIO, you need interrupts, you need DCMI. And then another thing you need to realize is that DCMI, you can't just handle buffers with DCMI. DCMI uses DMA. Okay? So in order to use DMA, you will need DMA drivers. So GPIO drivers, interrupt drivers, I2C drivers, DCMI drivers, DMA drivers. That's already 6 drivers before we can use these two little devices together. Before you can pipe signals from this little camera into this device. Okay? Before you can basically point your iPhone at something and get a, so let me see. I'm just getting my phone. Cool. So if I have an iPhone like this and I can point this, I can point it there, and if I point it at myself, you can see pictures of me on the screen. So before my image gets sampled by the camera and then it gets into the camera and it gets to the screen, we're not even dealing with the screen right now, okay? We're not even dealing with the screen yet. you already have those 6 sets of drivers. That's already 6,000 lines of code. So as you can imagine, Paul, if you want to make it sort of automatic that you can make it sort of automatic so that you can operate these devices, the pull requests are going to be huge, because you're going to need all of these little subsystems speaking in tandem, and they're going to be, there's also something called isochronous. So they're going to be speaking in tandem, and it's going to be depending on timing. Bartholomew is very familiar with this because we did some audio work earlier this year. Like this, you get the samples, and then you need to do something that is called image signal processing. So again, let me go and add another thing on top of it before we go to the next one. So there's a program, there's a library called LibMP. LibMP is a what is it? LibMP is a image signal processing software. So what LibMP does is these data signals that come from the camera, these data signals. So there's this D0 to D7. It's an 8 lane bus. It's sending us samples from the camera. The way the camera works is like Omnivision. Yeah, let's look at this. So the camera has an array of ADCs. Yeah, and the array of ADCs does something that is called sampling. So the ADCs look at a scene. Actually, let's look at a Bayer filter. That's better. Bayer filter. Bartholomew has had me talk about this so many times. So this is actually how a camera is. It's half green, quarter blue, quarter red. And this is because our eyes as humans are very sensitive to green. We don't know why. Well, some biologist knows why. I don't know why. I'm a computer person. So the camera will look at a scene, and then each of these little boxes that you see is an ADC, an analog to digital converter. I'm going to even assume that is abstracted away from us. So we're not even dealing with the ADCs here. Someone is doing all the ADC work and is just giving us the digital data back. So the camera will look at a scene, and then each ADC will sample. Each ADC is a filter. So it's a green filter, and then it's a red filter, or it's a blue filter. So if it's a green filter, it will sample green light. If it's a blue filter, it will sample blue light. And if it's a red filter, it will sample red light. And what these lights are is just wavelengths of radio signals. So if it's hit by a certain amount of a radio signal, it will react in a certain way. The ADC will read a value. And it's actually really easy to look at it if you look at this this Omnivision document. So let's actually go see here. Isn't it here? There's a graph. There's a really nice graph that shows you what images are. Very cool. So light is wavelength from, well, colors and light itself. Light is a radio wave. Light is an electromagnetic wave. Okay? And colors, as we perceive them as human, are electromagnetic waves between 300 Newton meters to 1,000 Newton meters. Okay? And 1,000 Newton meters is towards infrared. We can't see that. And visible light itself is between somewhere between 350 and something like 650, 750. And that's why you hear there's a sea animal that can see more colors than us. That's because they can sample more ranges of Newton meters. So this is within the camera. And what you can see, the blue light has a certain wavelength, the green light has a certain wavelength, and the red light has a certain wavelength. So what the Bayer filter does is all of these little boxes will sample each of these colors. And then what will happen is it will collect all of these colors in the way image 2 is, but it won't collect those colors in it won't collect those colors in, it won't tell you the color, it will just tell you how much it collected. Now, once it does that, the filter pattern will be looking like this, RGBIR. So the filter pattern will look something like Bayer filter pattern. Let me find it for you. I think somewhere like here. This is where I looked at it the other day. So we want a biggish one so that we can look at it. We can imagine what a camera sees. Let's even look at this. So cool. So it's like this: blue, green, red, blue, green, red, blue, green, red, whatever. And then that will sample blue light. Let me actually zoom in so that you guys can see. Sorry. So this will sample blue light, this one green light, this one red light, this one green light, and so on and so forth through this whole array. And it will give you all of these values. And then what you have to do is something called image signal processing. And image signal processing is take all of these numbers, you will take all of these numbers and you will compress them into one color. Okay? So that's why we get RGB. You get an R value, a G value, and a B value, and then you smash them together. I don't know if anyone has taken some art classes, maybe in primary school or elementary school. You remember, like, there's primary colors, and then there's tertiary colors, and then there's all of this above tertiary and all of this. So you combine all of these primary colors and you make them some color. So you will Bernard, you will so what you will end up doing is you will compress all of this information into a small you will take sets, you will take groups. So usually we do it, if it's RGB, we will do it 3 by 3. So you will take this 3 and this 3, and then you will compress all of this box of 3 here into 1 pixel. So the red will be this value, the green will be this average of all of these values, the blue will be the average of all of these values. And then you will call this 3 by 3 a pixel. And then you will take this next 3 by 3 and you will do it. And then you will take this 3 by 3 and do it. And then in doing so, you will have started with 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You will have started with 25 readings, and you can compress them into 4 readings, 4 pixels. I'm going to take a sip of water and then I'll come back. Any questions so far? Cool. I'm either going too fast that it's confusing, or I'm going comfortably slow that everything is obvious. I hope it's the second one. I also don't know this stuff. Just please remember this. I also do not know this stuff. I'm just learning it along with you. So, I think the question I was alluding to answering is Paul's. Paul is asking, why is that PR so huge? 95 plus 5 changes. So, the thing I'm trying to show you is that in order for us to use cameras, to use media that we are used to, we need to, what we need to is we need to do multiple things. We need to use so many drivers so that we end up seeing, like, an image is something that has come through a lot of work. You have to sample the pixels, you have to sample the filters, mangle the filter readings into pixels, arrange the pixel readings into a buffer, give this buffer into something like a graphics library, and then this graphics library can now push the it's fine. Who doesn't know about it? Push the images out into some, push the images out into some display of some sort. That is why, Paul, I hope that answers why this tab, I'll close this tab, it's fine. Paul, I hope that answers why this PR is so huge, LibMedia MP. And I think before that, so I've sort of explained. What I've sort of explained to Paul is why the LibMedia pipe is so huge. So now we can. It's been actually a very good 20-minute introduction into what is involved in showing media, collecting media from the world and showing it to someone else. And the same is, remember, I just touched on the camera and the way the camera works, the way it gets video and the way it shows you video. I haven't touched on the way the microphone works, which is something that Bartholomew is going to be very familiar with. So let me see if I can show you a sample. I have a sample somewhere here. I'm right next to my desk. I'm just collecting a piece of audio from somewhere. I would like to show a sample audio application that I have somewhere here that we built with Bartholomew. Bartholomew, can you upload a picture of your sample? I am trying to find this sample and I'll show it just now. Yeah, I found it. Cool. So, this is same. This is how audio works. You have a microphone and you have a microcontroller, and then there's data going from the microphone here into the microcontroller. And the same story with video. You have to sample the audio in the microphone. You have to get the audio gets to you as ADC readings. You have to combine all of those ADC readings into audio samples, and then once you have those audio samples, you have to now change them back into some audible audio for us. Same thing for display. I have a display thing over here. I can't really move my hands because I need to use both of them, but the same thing. It gets a buffer. You just get numbers. And then all of these numbers have to be transformed into either sound or colors or something of the sort. And that's why this PR is so huge, and that's why LibMedia pipe is it's a groundbreaking thing, because previously there's all of these individual things already. What we need now to do is to build all of this glue code that makes everything work together. And the other thing I was alluding to, or the thing I was going to explain as well, is that Zephyr itself is the same thing. You have drivers, you have subsystems, and all of these things, they build up together, and then they build up together into giving you a whole thing that you can use together. So when you're doing bare metal stuff, you would build a GPIO driver, DMA driver, this device driver, and you would use all of those separately, one by one. And your main application ends up being quite a huge application, as you can see in the repository I started to show you. So these are just drivers. And then if I go into my source and let's look at, say, something like LED toggle, just even an LED toggle, there's all of this. That's quite short. Let's look at SPI-TX maybe. So it's using all of these individual libraries and setting things up so that you can actually put them together. Chiefly that is what Zephyr is. It's glue code for all of these things that you have to build up together so that you can use them. Cool. So let's go back and keep exploring libmedia MP. So here's a presentation. So video for Zephyr. This is basically what we're doing, from basic APIs towards fully fledged video subsystem. What's the next thing? So the original video for Zephyr APIs we have video device tree bindings. So that is the device tree for image sensors. We have a video control framework already. We have video buffer management already, and support for M2M devices. Okay, and then those things, they exist already and they work already. But really, what we want to do is so this is how it works. You have an application, you have a video device. The application asks the video device, what capabilities do you have? What resolutions can you show? and the video device replies, and it tells the application, this is the resolution, this is the frame rate. And then once the application knows that, it sets the format, it sets the application, the video format, it sets the frame rate format, the frame interval and things like that. It sets the buffer sizes, and then, you know, now the video device knows what the application wants from it. It knows, I need to draw a picture this size, I need to draw a picture every so often. So you can do 60 FPS, you can do 40 FPS, you can do all of these FPS as you don't know, you know. So, and then once you've gotten all of those settings and the video device knows that, okay, cool, I am set up for all of this, then you start asking the video device, now send me frames at the frame rate and at the frame size that I have asked you to. And this is what it does. And then now you basically have this thing that's called video start. Video start is, there's no such thing as a video device. You have something called an image sensor. And then every so often you can take an image. So if you're taking, if you need a 60 FPS video, 60 times a second, you will grab a frame. So, and then you will display this frame. So every, you know, you will sample a frame every 60 times a second, and then you will display the display is another thing in itself. And this is what is happening. So you will pile all your sampled frames into some box somewhere, and then once something is consuming them, you can put them on the network, you can put them on UVC, you can put them on whatever way you want to do. You can put them on some sort of display device, and then now you basically have a queue. You push into the queue and you pop out of the queue. You push into the queue and you pop out of the queue, and that is queuing and dequeuing. And this is what you still had to do this very manually. You still have to do this very manually. Let's look at how a normal video application looks like. My phone's vibrating and it's distracting me. So let's look at the samples. And then drivers. Samples, drivers, video. I think I just worked on this probably. Cool. So samples, drivers, video. Let's look at capture. And yeah, and then let's look at source. And then let's look at main. So good. This is gonna be some giantish file. So exactly. This if you have display, we're not dealing with display right now. So the first thing you need to do is you need to ask whether this is, yeah, I don't want to do app setup display. I don't want to do setup video selection. So the first thing you're going to do is you're going to ask the video, tell me what you're capable of. What frame rate can you do? What resolution can you do? And then once you do that, you will set a selection is you will decide how much of the frame you want to show. And then you will tell the video device. This is what is happening here. So if you want to crop, if you want to do something, if you want to scale, if you want to stretch the image, whatever way you want to do with the image. And then once you do that, you set a target crop. Basically, you get a selection. You set a selection of the video. And then after that, what you're going to do is you're going to set the selection, and then now the video device knows what is happening. So if we go back into here, what we've done so far is go all the way to here. You've allocated a buffer, you've set the format, you've set the controls. That's cool. So the next thing we need to do, I think this is used in the previous step. This is what format can you do? This is the format I want. This is and such and so on and so forth. And all of this is setup stuff. So if I go into the main of the application itself, here, I want to look at that. You query the video information, cool. you have the video information. It's in if ret is successful, cool. It's going to go into format, and then based on format, you will set up video selection, and you will again set it based on format, and then you will set up the video format, and then you will set up the frame interval. The frame interval is how many times you get a frame per second or whatever, however way you want to do it. And then you'll set up the video controls. Are you going to do a stop? Are you going to do a fast forward? And all of those things and whatever. Rewind and sort of that. And then if you have a device, you're going to set up devicing and such. Yes, I'll answer that just now. And then after you do that, you're going to set up the video buffers. And then once you've set up the video buffers, you're going to start the streaming. And starting the streaming is pushing into the buffer and popping out of the buffer. And while true, you're dequeuing, and the video subsystem is enqueuing. That's basically what is happening right now. What is happening in today's current version of Zephyr. So I'm going to stop. I'm going to take a sip of water. I'm going to take a chance for questions, and then I'm going to answer Paul's question. Any questions so far? Paul is asking a question. Does Zephyr have the concept of user space versus kernel space, like in Linux? Yes, it does. It does. So application side, this here, in this space where we are, this is user space. And then kernel space happens in Zephyr. So if we go to something like, if we go something like drivers, and then we go, actually let's just go drivers video. Let's go drivers. Come on, do I have such slow internet? If we go into drivers, and then if we go into video, this is what we're exploring. Everything in here is kernel space. So because this kernel comes with this driver, and then you choose them when you're doing something. So let's just go look at video common rather than actually looking at any specific device. Yeah. So let's look at video. No, not the H. Even though the H is inline and it's actually code. Just a moment. Video common. So operations happening in here are in kernel space basically, because due to the way you use the device tree and such, you do build, the kernel comes with the things you want, and then you can do stuff in the application on the other side that is using the things in the kernel space, or rather from the kernel. The application uses things from the kernel in application code. So let's go back to exploring the video for Zephyr things. So this is, and I'm rushing through this because I don't want to make it a 5-hour video, although I don't mind doing that. But the first thing we need to do is kind of like, I like explaining stuff, and I like it that everyone understands. It's not just a video for Bartholomew, because if it was just for Bartholomew, I would just talk about code, very deep code, and he would understand everything, but that's unfair to everyone else. Cool. So that is how video works. So again, kind of serendipitously, we go into Paul's question. So you have device tree. The device tree selects the camera, and you select the camera. You say obviously 7670, and then you tell the board the camera is on pin so and so to so and so. Okay, so here the sample application we're looking at today, we have an OV5640, and then the camera is on the DVP connector. And if you look at the code that I have here, that I don't know if we'll get to running, we will try and get to running it. If you look at the code that we have here, and you look at the app overlay, so you will see here we have DVP 20-pin interface, and then that DVP 20-pin interface we have the OV5640 camera. Cool. So device tree, it initializes the driver, it initializes the video subsystem, and it checks, it basically makes sure it initializes the driver before it initializes the video subsystem. And the difficulty here is to make, to model complex camera pipelines. Some people need to use more than one camera. You can have, like, the stream you're watching right now, think about it. There's a webcam view and there's a screen view. So that's already more than one camera. That's already a complex subsystem. And then think about it. It's two different streams, because there's a video stream that is coming from my webcam, yes? And then there's the video stream that is coming from my screen. And then these all have to be sort of joined in a certain way that me, the user, has decided. And then this is being pushed out into the network. Okay? So when you're dealing with like very naive or very basic bare bones structures like this, it becomes difficult to start doing complex things like that. And the aim of LibMedia Pipe is to do things, to make things like what I am doing right now on this stream very easy. We're combining two video feeds, and then you combine them, and then you don't even actually have, whereas I have OBS and I can see what I'm streaming, I don't necessarily need to see it. I need to send it somewhere else. Okay, cool. Any questions so far? So that's the first. This we're now exploring how the current system works, and then we will build up towards looking at what LibMedia Pipe actually brings in. Okay, so we have video device tree, and video device tree is just, they tell us what camera it is and where it is on the board, which pins is this camera using, and what camera it is. Okay, and then you usually have something that is called a port, but because ports don't translate from Linux into Zephyr just directly. In Zephyr we call them endpoints. And an endpoint is basically, if you remember correctly, if I remember correctly, I was showing OV56 here, OV5640 here. An endpoint is how this this databus gets connected to this databus. So you have the way you're controlling the camera and the way the camera is sending you data. And the way you join them is you're using endpoints. You're basically telling Zephyr that 8 lines of data that is flowing through there is actually associated with these messages that are coming from here. So that's an endpoint. And basically the way you're linking them, as I'll show you here, so you see we have an I2C interface. This is the SCCB. And then this SCCB is called, it has an endpoint EP out. And then there's a 20 pin interface, and the 20 pin interface has an, endpoint in, and you're joining them using endpoints. Basically, is what the thing is saying here. So the two endpoint nodes, I will zoom again so that this is more visible. 2 endpoint nodes must be linked with each other via their remote endpoint P handles. However, Zephyr does not allow circular dependencies, so direct P handle references are currently not possible. A remote endpoint label string is used instead to be able to specify at least the label of the peer remote endpoint. Okay. So, and here is, if you go to the Zephyr, actually, I really want to look at this. Oh, that was a link. Nice. Cool. So this is where ports come from. Wow. A few weeks ago with Bartholomew, we discovered where they're defined, and now I have discovered where they're actually built. We discovered where they're defined in a board or an SoC, but now we're actually seeing where they're built. So basically, these are the ports. You join them, and you send data from here to that one to the other one and such. Cool. Just post any questions you have so far, and then we'll keep going. And I think I can just go back to where I was. I think I was somewhere like here. No, somewhere like here. No, actually the next one here. So you can get a device, a remote endpoint with device DT-get, remote endpoint, and this is all used inside the video subsystem. If you're going to use it, it's not going to actually be used. So here's, look, OV5640, this is a sensor. It pushes to a MIPI-CSI-2RX receiver. So MIPI-CSI-2RX receiver is like this one here. This is a MIPI-CSI-2RX receiver here. And this is on a STM32 and 6570 whatever. So the camera, data comes from the camera. Here you go. This is an IMX219, and it goes along this FPC cable, and it comes into this MIPI-CSI-2RX. On the NXP that I have on my desk right now, we're using SDMA, and on this one we use DCMI. And then this receiver gets the stuff and it puts it into DMA, and then it pushes it into memory. This is actually the process that I was explaining earlier. So you have a sensor, and then the sensor, you have a camera interface, and then from the camera interface you have DMA, like this data pipe, because you can't do polling, it's too fast. And then from the data pipe you have straight into memory, if I explained correctly. So, and then you have device tree. You define your camera, and then you also define your this is going to be defined in either your board or your SoC, and this is also going to be defined in either your board or your SoC. And you're pushing, so you have a remote endpoint label here, and then in MIPI CSI you have a remote endpoint label that pushes in, and then here you have a port 2 that pushes out, and this out goes into here, and then from this in you actually push to DMA, and DMA. Now this data magically appears from DMA. This is in Zephyr. If you're doing this bare metal, this would all be individual code and drivers that you would build together. You would patch up together to kind of work with this. And then what does the video control framework do? Drivers need to handle much of all the work, while much of the code is not driver specific. This is today. You cannot query mean, max, step, default values of a control. So what is the maximum width? What is the maximum height? What is the maximum exposure? What is the maximum frame rate and stuff? Okay, cool. I will answer that. So drivers are kind of basic right now. They're sort of dumb. Okay, you can't do that much with them. So drivers don't need to implement get control APIs. Right now they do. Only drivers owning the controls need to implement set or get control APIs. That's fine, and support composite group of controls dependent on each other. And there's some documentation that would make this video for Linux docs. So there's some documentation here that would make it, if you find time and you go through this video for Linux API, you would understand quite a lot of what I'm explaining, and they would actually go through explaining quite a bit. And there's also an interesting article on LW. I'll put all of these links in, so let's actually just put them in the description so that people can have them later. This is links here. So that's a pull request, and then after the pull request, let's remove this ZDS link. While I'm putting this up, please ask questions. So that's a Zephyr developer service link, and then video for Linux docs. V4L docs. This is all in the description if you're watching this later. And then there's also an interesting article from LWN, which is LWN.net. Complex cameras. So there's a journal, coping with complex cameras. Check, yeah. So this is also another. Look at this. Look at this. It's a. I think it's a minute group of. It's minutes from Zephyr. Not from a Zephyr. Coping with complex cameras. So this is minutes from Linux get together where people discussed what needs to happen with in respect to cameras in Linux. So this is all in the description already. I put it up. I'm going to take a sip of water or tea. Okay. Paul says I should do a Zephyr 101 series for guys who have never done any embedded web guys. Yeah, I will. I'm very welcome to do this. Sure, no problem. I can. Most of my videos I always attempt to do it as though I am doing a Zephyr 101, but I can also, I can also make it very simple. Like jumping straight into cameras can be quite scary and very complicated. But yeah, I can probably do that. Yeah, I can probably organize to do a video series on Zephyr 101. There is Bartholomew, if you don't mind, can you link into the description Fields? Is it Fields or? No, not Phil Salmoni. Who is it? Sean Heimel does a very good. Actually, I'll just show it to you here instead of. So if you go to YouTube and you look at the best introduction for Zephyr is to build a Zephyr driver. If you build a Zephyr driver, you will sort of end up understanding Zephyr very easily, and it will be difficult in the first place. So Sean Heimel, Zephyr. So there is a video series by Sean, but it was in version 3, so that might have changed already. But it's maybe a couple of months old or maybe 3 months old. But there's a DigiKey series into introduction of Zephyr. It is a 2025 one. This is a good one as well, and it's a group of like 12 videos that are really, really good for understanding Zephyr if you want. But if you would prefer that I am the one who does a introductory series, I can always do that. That's not a problem. So check out this series by Sean Heimel, and if you have any questions, there's a link to the Discord below. Join our community, jump in and whatever. Cool. So let's keep building up towards LibMP. So we've looked at what drivers do. Now let's look at what the video control framework does. So remember, video is made up of quite a few subsystems. There's the devices themselves, and then there's a control layer, and then there's the application layer. We have not even when we get to the application layer, that's when we realize how the LibMP actually is quite nice. So what the current aim for Zephyr Video, if I might speak for that team, which I'm quite close with, but I wouldn't go so far as saying I'm the one who speaks for them. I might also be speaking out of turn, so it could be different. But what the current aim of the video team in Zephyr, Alain, Joshua, Fee, and Leach, and all of those people, and myself included to some extent, what the current aim is to try and build a control layer that is quite similar to what Linux has. You don't always have to invent new things. There's people who have done what you're trying to do, and in probably very good ways. So what we're trying to borrow a leaf from Linux and to see if at all possible we can actually implement their system or some subset of their system the way we and use it in video for Linux for Zephyr. So it's going to feel very similar to what Linux has, and ultimately what the aim is to have a pipeline that can go all the way from a microcontroller up into some Linux device. And this will be very interesting because now you can do stuff like you can sample on low power, and you can do basically you can have microcontrollers out there sampling video, and then you can have Linux subsystems or Linux systems themselves actually doing machine learning or inference or sort of like computer vision devices themselves. I don't like the term AI. I don't think AI is a thing. AI is a philosophical discussion. I prefer to call it things like computer vision and computer aided vision or machine learning and such and things of it. So I prefer those because I think artificial intelligence is a catchy term, and it's a philosophical discussion, not really maybe not really a scientific one right now, but eventually I'm sure there's people who can make it scientific, and maybe I just don't understand it enough. So the video control framework, you have a video device defined. So this will be in somewhere like, I'll show you now. Let's go and look at an actual video driver. Let's look at the OV5640. That's the one we're using right now, although I'm very familiar with the OV7670 as well. You have this macro at the bottom. So there's this macro at the bottom that this is init, but I want to look at video device define. Video device define. Control F. Video device define. So there's this macro over here, and this macro basically registers that a video device has been logged onto the system, so that whenever this device is initialized, you can see that whenever this device is initialized, you can actually access it from the video subsystem. So in the driver itself, you define it both as a device and as a video device, so that the video subsystem can see it and start using it, or rather the application can use it via the video subsystem. That's basically what is happening here. So video device defined in addition to define DT-ins define in a RAM iterable section. And an iterable section is basically I'll just Zephyr sections. It's a fancy thing where a script goes through all the code and collects all the structs that have been defined as devices and puts them in a place where they can be reusable. So this page contains reference documentation to the iterable section APIs, which can be used for defining iterable areas of equally sized data structures that can be iterated using struct section for each. So maybe you want to add 5 cameras, maybe you want to add 5 microphones, maybe you want to add 100 GPIO pins, and iterable makes it so that you can define one and then you can, use it. It's iterable. You can use it through a loop, but it's iteratable. You can iterate through them. Basically, that's what happens. Any questions so far? I'm slowing down, I realize. Okay, cool. So we implement the driver the way one implements a normal device driver in Zephyr, and this enables us to use the image sensor as a device driver. And you would just implement the controls. You would basically implement what the frame rate is, let's actually go and look at it. It's easier if we just look at it. So when you're implementing a driver, I don't like looking at video drivers because they can look very complex, but they're not very complex really. I want to look at let's look at the IMX35. This is the newest one that I'm very familiar with, and this one is done by Alain, who works at ST, and Alain is, in my head, like a genius or something. So you enable someone to set the format, you enable someone to get the format, you enable someone to get the capabilities of the device, you enable someone to set the stream, either start the stream or stop the stream, You enable someone to set their gain, which is exposure and things like that, and then you enable someone to set their what is gain? Gain is gain is how much to white balance basically. I could be speaking wrong. Yeah, but it's a color correction thing. You set how much you want the color to be boosted or something of the sort, and then you set the control exposure. So you want how long do I open the pinhole camera and close it and sort, and then you have a set control that enables you to set the gain, the exposure, and all of the other things, and you can get the frame interval, you can enumerate them, and then you have a device API that allows you to expose a function for setting the format, getting the format, get capabilities, setting the stream, set control, and then the frame interval is fixed, so those are not here, and then so basically it's the same one, and then enumerate gives you all of the options, and then you can also do some stuff like control the input clock and stuff of the sort if your camera has that, and most cameras are different, but most cameras will have some sort of is it a peak clock? It's probably a peak clock pin. You can see it here. There's a peak clock pin over somewhere here. So that's this is an output. There's probably going to be an input, which is an M clock somewhere. X clock, yeah, system clock or something like that. So these are all clocks you feed in or you get out of the camera so that you know how to use the thing. Cool. Not you, well, the device. You know how many frames. Remember, all of this is isochronous. So there's timing dependencies on everything here. Cool. Let's look at something else. Cool. So this is how you implement video control, video device. And then as we looked at the video controls application, this exposes controls back to the application. I think I don't know who was present. Maybe Bernard, maybe Bartholomew, and maybe Nathan were present when we were doing this. But whenever we debug camera devices, whenever we do a debug session and we're going through a camera device, we have to jump through between video common and the device driver itself and such of the sort. And basically what you do is, what you realize is video common actually calls to the device driver, and then actually the application calls to video common. The application calls to video common calls to the device driver. It's like this basically daisy chain of control going backwards. And so video query control would ask the camera like, what are you doing? What are you capable of? And I can show you this sort of information right now if I actually find a thing here. So cool. So there's this. So I will reboot this device so you can see them come up. Cool. And then I will do Control A, and then I can press up, I think. Control A, and then this, and then I can just go up. So let's actually go look through this. We boot into Zephyr, and then we see the video interface is video SDMA, and then we see the capabilities over here, and then the capabilities is basically we are doing RGBP, which is RGB 565, and then we are doing a width of 320 and a height of 240, and the max and the mean is 320. It's basically set. And then you can see the video format is picked up as RGBP, that is the format, and then the width is 320 and the height is 240, and then it shows the supported frame intervals. Video source does not support frame rate control, so this is as SDMA specific something. If I were to run on my what is this? The STM32N6, we would see completely different details. And then we have supported controls. It would tell you how much. It depends on what you want. So here, let's look at the supported controls. So it tells us which device. We are looking at OV5640 at address 3C, 0x3C, because it's a I2C device. And then you have a brightness control, you have a contrast control, you have a saturation control, you have a hue control, you have a vertical flip control, you have a power line frequency control. And then you see It has all of these other controls. There is disabled, a 60 hertz, a 50 hertz, and an auto. And then we have an analog gain. We have a pixel rate. We have a test pattern. This is if you wanna, you don't necessarily want to try and get the video out. You want to actually generate some sort of test pattern just to make sure that the sensor works in a way that you expect and such. And then it will tell you we have a display device, and then it will look at the capabilities of the device and the resolution of the device. So I have right now I have connected an ST7725RS device, 27S device, LCD display. It's a little 80 by 160 display, because earlier today while I was trying to hook up this one, I broke this one. This is the one we would have used today. Cool. So this is kind of what the video subsystem does. It goes through all of the, it looks at what your display can do, it looks at what your capture device can do, and then it sets all of this. It tries and does something called arbitration. It negotiates from this side to this side and tries to make them meet in the middle. Cool. So let's keep looking. So as you can see, we've actually looked at practical information here of what this happens here. Video buffer management, this is work in progress. I believe, let me see, can we open in a new tab? Isn't this merged? I feel like this is already merged. Oh, this is new completely. So this probably comes with video for Zephyr. And this is probably wants to rework the buffer management whole scale, so that, because the main thing you're going to change when you're going to change the video subsystem itself is how data is shared between the sensor and the display. Because the drivers will do the work that the drivers do, and the display drivers will do the work that the display drivers do, and the video drivers as well, and the DMA drivers as well, and the GPIO drivers. Those don't change. What you really want to change is how information flows from one end to the other. So I won't make this more deeper by looking at the buffer management with 38 file change, so I'm going to just leave it at that. And basically you can see that Phi is trying to enable us to have a simpler buffer management so that you can have it work. Dynamic allocation on the video memory heap framework holds a static array of all video buffers, and then I think if it's dynamic allocation, that means we are either using a K heap or a K slab, and you can only allocate a single buffer at a time. Application needs to keep the empty allocated buffer pointer, so the application is managing the buffering, and it tracks the buffering, enqueuing, dequeuing. This is what we were looking at here. Enqueuing, dequeuing of video is managed by the application. Enqueue. Yeah. So you need to keep track of which one is allocated, and you need to enable to push into the buffer and pop out of the buffer, or the stack of buffers and such. Cool. So, and then application doesn't need to keep the empty allocated buffer, can allocate it batch. Request instead of allocating. So cool. So this, I think we've gotten to a point where we're looking at the new changes that have been introduced by LibMP. And basically, video buffer management support user provided buffers. This is quite cool. Nice. So now what is happening here is, wow. So you can tell, now I understand what is happening. So one of the bigger changes here is that the video subsystem is not going to be managing the buffers. What is going to happen is, at some point, you will want to do stuff with the video, which is exactly like the stream you're watching right now. I told the webcam, just give me the video you're getting, and I told the screen, just give the screen recorder, just give me the video you're getting, and then it hands those buffers over to me, the user. And then the user, I myself, what I go in and I do is I go and give it to an application called OBS, this application over here, the Open Broadcasting software. And I enable the Open Broadcasting software to manage these buffers together. I mean, I could actually pull it into here. It would look very uncomfortable because it's gonna stream itself into itself. But this is how it would look. So you can see there's a big video recording, and there's an internal camera, and there's a laptop screen, and I'm recording from both of them. And basically what is happening is OBS is joining both of them. So user managed buffers is something that is being introduced by LibMediaPipe, and that is actually quite a big step towards having a MediaPipe library. I've been speaking for quite a while. Does anyone have any questions so far right now? Any questions so far? Or did I lose you guys completely? Bartolomeo, give me a thumbs up if you're around. Whoever's around, just give me a thumbs up. Let's see. Yeah. I just want to know that I didn't lose guys, and I'm just like, speaking to myself. Well, I don't mind speaking to myself because I'm understanding this as I'm doing it as well. Any questions so far? Cool. I think there's a lag, so you're only going to hear what I say in a bit. So, LibMediaPipe, it looks like LibMediaPipe attempts to give the buffer control to the user. And if it gives the buffer control to the user, what happens is, because you can control the buffers, you can manage them. Because if you give me a buffer of image or of a screen recording, then I can mix them up the way I want. And if I can mix them up the way I want, then I can do the sort of OBS thing is doing right now. And that's kind of what happens. So if we're supporting user-provided buffers, we enable people to control what they're seeing. And then you're basically switching from queues to RTIO. RTIO is another Zephyr subsystem, but that we have not looked at. We will look at later. But it basically is a DMA like it's real-time IO. Zephyr RTIO. It's real-time IO. It's a DMA like thing. Okay. Zephyr RTIO. Yeah. It's basically, yeah. You have a submission queue and a completion queue, and it just works with them together. It's almost like DMA. And this is also the reason RTIO exists in Zephyr is because DMA implementation from device to device, from family to family of devices, like from ST to NXP to Renaissance to Nordic, DMA is very different everywhere. Some people are using AXI buses, some people are using AHV buses. It just depends on the IP that they're using at the low level. So DMA is very different. So I think RTIO, I still don't understand it quite correctly, so I'm speaking under correction. But the thing I understand here is that RTIO is a software DMA sort of solution. It enables everything to happen in software, abstracting away all of this hardware stuff that makes DMA different and DMA difficult to handle everywhere else. Cool. So let's keep going. So we're moving from fast in, fast out buffers to RTIO stuff, and then I think M2M is machine to machine. RTIO, it seems as though LibMP wants to introduce machine to machine, which is cool, which is kind of, so video buffer type, new transform caps, and what is it? Pretty straightforward at low level. Yeah, of course, Fee. Everything is straightforward to you. You just wrote it all. Let's look here. So, memory to memory. Okay. So supporting from memory to memory device, which is exactly the same thing we've just talked about. Memory to memory is when you're doing something like taking two buffers that are in memory, and then you're joining them into some sort of other buffer that is also in memory, as you can see. So if you want to support things like memory to memory, video transform, which is exactly what I've explained right now. The thing, I am streaming 2 video streams that are both, my screen recording is going to some section in memory. My webcam recording is also going to some section in memory. And then what I'm able to do is chain them together or combine them in whatever way I want. So let's look at it here. Camera sensor, camera receiver, DMA, memory, transformer, M2M, memory, display. As you can see, so the application is sitting in the middle. It enables us to join buffers that are in memory. That is what LibMedia pipe is going to do, and such. And okay, cool. Finally, we're down here. So you have a video for Zephyr source, which is a camera, and then it's a source pad, and then you have a sync pad, which is an application, and then on a display you have a source. In the application, you develop a source pad, and you send out to another sync pad, which is a display. So basically, on this side, the camera is the source, and the application is the sync, and then on this side, the application is the source, and the display is the sync. So what is happening here? What is really happening is, what we're being told is, we can have buffers. Our application can be given 5 buffers, and then it can decide what it wants to do with those buffers, and then it can send those buffers somewhere else if it so wishes to do that. So let's look at it. MP init, MP element source. You say, oh, it's coming from a camera source, and then you say you make a transform. A transform is how you're going to join it. Exactly. Again, I refer you to the stream you're watching. The stream you're watching is a webcam stream and a screen recording stream that have been transformed to be joined together by OBS. So it enables the application to do the joining of the 2 streams, and then after it's done all of that, the sync in my case here is some network somewhere. So this is pushed out to a network somewhere. Okay. And basically you create the elements, you create a source, you create some transform element, and then you create a sync, and then you set the element properties, you set the source for the properties, you set the properties for the source, and then you add the elements to the pipeline. You add a pipeline, you have a source, you have a transform, you have a sync. I don't know what the null at the end is, and then you link all the elements together using MP element link, and then you start playing. You set state MP, set playing, it's streaming, it's playing, it's whatever. Basically, that's it's a long-winded way to say that we can basically start using one buffer, and we can join these buffers as we need to, and then we can share those buffers after we've done stuff on them, basically. So the thing is, new video APIs, we will have frame rate changing, crop selection. Crop and selection is exactly what the video you're looking at right now is a composition of 2 videos. There's a screen recording and the webcam recording, and then I've cropped out the bottom right of some section of the screen recording, and in that I've put in the webcam selection that I'm showing you right now. So it's been quite long. Thank you, and questions. It's been quite long, and I won't keep it going much longer. I think I'll leave it there for today, because we've walked through the motivations of why one would build something of the sort. We've walked through the reasons why we would build this. Display a frame on the LCD. Bartholomew, my LCD does not work. Let me show you. But you know what? We can probably use SW generator. Why don't we use, Bartholomew wants me to run this so that he can see it work. Why don't we use SW generator first? Let's actually just pull the pull request and try and build a sample, no? Because Bartholomew wants me to build a sample so we can see. Trust me, I also want to see how it looks like Bartholomew, so don't worry about it. So pull that. And then I will show you the real life. Check out as you can see, this is how the developer you're watching right now works. I Google stuff. I think it's checkout, blah, 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 blah. Yeah. Let me copy that. And then I'll go here. Okay. I'll go out. I'll go into Zephyr. Let's check out that pull request. This is how fresh I am. I have not even pulled down that copy. Okay. And then what I want to go and do is get the pull number. Copy. This is all fresh completely. Like I have not but I have known about LibMP for quite a while, so I've been expecting it. LibMP. RFC, LibMP. Okay. Okay. Git check out RFC. Okay. And then I believe there's going to be some samples somewhere here. Yeah. Yeah. Let me see. I think he explained somewhere how to build it. There's gonna be a way to build it. Let me just find out. Files changed. Once I get an LCD working, we will do it. Maybe we'll do it the next stream, Bartholomew. As always, you know, sometimes it takes a while before we can actually run something. We have to do quite a few steps. Yeah, sample subs is audio. I don't want an audio sample. I want to look at video examples, camera display, camera transform display. Yeah, this is actually a good one. Can I do that one? So video example, sample subs is LibMP. Okay. CD samples subs is LibMP. LS, and then CD video examples LS, and then CD camera transform display LS. And let's look at this. Let's see if we can use perhaps we can use video SW generate so that we can actually run it. I want to do it on native sim if possible. I guess there's not a way of doing it in native sim. Just a moment. Let me ask Fee if I can actually run it on native sim. Yeah, someone's helping me. Someone's giving me a command I can run, and then we can look at the sample. Oh yeah, just like that. Really? Best. tabs, cd, Zephyr, samples, subsys, LibMP, video. Yeah, I know. Okay, video examples, camera transform maybe. Wait, let's actually look at camera display. Let's just look at that one for now, and then yeah. Oh, I see what you mean. I actually wouldn't be able to do that then. I actually wouldn't be able to do that then because I would need to use my webcam. Okay, I can actually use native sim. Okay, yeah, I can use your native sim. Let's go with native sim. So that's west field dash b dash b dash b. Yeah, instead of this, let's actually go native sim, and then let's just go. Let's remove all of the other stuff, so we just build the one that's here. Generator. I've been told to go ask. Yeah, push. Yeah, just a moment, guys. Yeah. I need to just one moment. I need to mute my mic because I don't know who's coming. Okay. So it doesn't build yet. Bartholomew, why don't we go and figure out how to build this application on the Zephyr video channel, and we'll see how we can get it done. Is that okay? And then we can find a way of running it on native sim so that we can all discover, and then we'll come back and run it on the stream later together. Yeah, so once of all, thank you all so much for coming. Thank you so much, Bartholomew. Thank you so much, Paul, for showing up and hanging out with me today so that we could do this. I will actually do a few more streams of LibMP so that we can actually get it working completely. The first thing I need to do is get my LCD working so that we can try and maybe even put 2 cameras or something like that, or find a way of editing it together. But Bartholomew, let's take this to the public Zephyr channel so that we can actually find out how to run LibMP. Thank you. Thank you all so much. That was amazing hanging out. See you next time. That's amazing. Cheers.